Howdy, howdy. Hello, everybody. Welcome, welcome. Hope everybody's having a good day. Welcome, 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 welcome. So we're gonna do normal question and answer until 10, and then I'm going to switch over to, so that's for another hour and 15 minutes or so, and then I'm going to switch over to only members, subscribers can ask questions, and I'll also bring up guests. So if you want to ask questions, if you want to, if you want to come up and ask some questions, make sure to wait for another hour and 15 minutes or so, and then I'll be bringing up guests then. Right, let's get to some questions. Are you knowledgeable enough about quantum computers to speak to a few laypersons on a podcast? Perhaps. It depends on what they're asking about. Is there a way something can travel faster than light? Not if it's right next to you. There's no way for something that's like moving right past you to be traveling faster than light. No. Am I a member? I don't know. Do you have access to the emojis? Starfleet Academy greater than DS9? Well, I haven't seen Starfleet Academy, so I can't say, but it sounds wrong. Why don't electrons fall into the nucleus? Because they're not, it's not a particle moving in a circle, right? It's more of like a cloud, it's like a stable cloud surrounding a nucleus. Do derivatives stay the same along different axes in conformal hypersurface geometry? Do they stay the same along different axes? I mean, like so derivatives of a function, those are invariant under rescaling, so yes. However, and that's just because the function is not changing, right? However, the coordinates might change, which is, a totally reasonable thing to do. Like your coordinates might stretch or whatever. And also, derivatives of vector fields don't change, or do change rather. They're not invariant. Oh, Have you thought much about gravitational waves beyond quadrupolar waves for a full nonlinear wave equations? Well, so I haven't. That's not something that I'm particularly interested in, but people have, yes. Does the universe regularly convert energy back into atoms? Not really. This is not a common thing. What's conformal geometry? I know that's your research, but I don't understand the Wikipedia. So conformal geometry is just the study of geometry. I mean, you know what geometry is. That, in some sense, it's the study of those things about geometry that change in nice ways or don't change at all when you stretch and squeeze things. Can you describe quantum entanglement and how spin can change? So these are two kind of different things, but sure. Quantum entanglement can be thought of as like a kind of a fixed correlation between two particles in a system, where if one of them is one way, the other one necessarily is the other way. Now, that doesn't mean that they're communicating to each other. It just means it's just like a feature of the system that they have to be correlated that way, for example. Now, often we correlate spins with each other, so you might have one thing that's spin up, the other thing spin down, for example. And so, if one is spin up, the other one's spin down. If one is spin down, the other one's spin up. So that's one way that you can do entanglement, but it's not the only way. From Bacon and Bush with the $10, wait, you'll bring up guests, like Ask a Physicist guests? Yes. After 10 o'clock today, I'm going to bring up some guests, just to, probably 5 or 10 minute maximum, just to ask some questions in person. I need to figure out a way so that only members can become guests, but that's the idea. You talking Richie Flow? No, I don't work with Richie Flow. Why does string theory, M theory need 26 dimensions? Well, so bosonic string theory needs 26 dimensions because that's the only way to make sure the conformal anomaly vanishes, which is essentially one of the required features of string theory. conformal anomaly is just that if you rescale, and this is going to sound very, very technical, but there's something called like a world sheet for a string, which is kind of like the path through space-time that a string traces out. And that has to, the properties of that world sheet have to remain unchanged when you do a rescaling, which means that the conformal anomaly, and this is true even in the quantum theory, the conformal anomaly has to be 0. The conformal anomaly in some sense captures how much the physics changes when you rescale the variables in the world sheet. And it turns out that the conformal anomaly depends on the dimension of the space-time. And so in bosonic string theory, it works out that you need d over, it's d minus 2 over 12. Sorry, it's d minus 2. It's something like d minus 2 over 12 minus 2 or something like that. It has to be 0, where d is the dimension. And that's how you make the conformal anomaly 0, so you need 26 dimensions. It's been a while since I've actually worked that up, but where will you be pulling up guests from? All platforms, just TikTok, just curious. Oh, this is a good point. So I currently don't have a way to pull up guests from anywhere except TikTok, but what I can do is I can add let me add to my text chat where to join from. Here we go. Wait, no, that's the wrong one. Sorry, just 1 second, everybody. Is there like a white one? There we go. So this is the link. Text. That's the link to join. I'm not taking any guests there yet, so I'm going to hide this. But that will be the link to join. So I can take guests from anywhere. Which means that I need to go join on Discord. Okay. Anyway, let's answer some more questions. What do you think of the recent paper on baryogenesis of primordial black holes? I literally just saw your video on this, Mike, so I haven't read it. I can't comment. Like, I saw it 5 minutes ago. Seems interesting. I'm a little bit skeptical because generally, and obviously I'd have to look at the paper, but generally the idea is that the rate of CP violating interactions are so low that we're not even, like, we are orders of magnitude off from the amount of CP violation that we need in order to produce matter, more matter than antimatter, or the amount of matter that we have. And so, like, I'm a little bit skeptical that, you know, evaporating primordial black holes could produce enough CP violation in order to do that when we're so many orders of magnitude off. From Bacon and Bush with the $10, you've explained what Einstein meant by speed of light is the same for all observers, which is super insane. Now, why does that matter? Well, it matters because if it's true, then there are some questions we have to ask. Like, I mean, you can ask the standard question. If you're in a car moving at half the speed of light relative to somebody on the ground, and you shine a light beam, how could it be? What facts of the world have to be true so that we both measure the light moving at the same speed away from us? Both me, the person in the car, and the person that, you know, standing on the ground. So the implications of this is that it must be the case that both time and distances change with respect to one another, or with respect to the observers. And this is how you can actually just derive Lorentz contraction and time dilation from this fact. Best textbook for differential geometry, particularly for applications in physics. Let me see, 1 sec. So I thought I had a hard copy. It might be at my in-laws' house. But there's a book called Geometry for Physicists. Or, sorry, no, it's not called that. It's called The Geometry of Physics by Theodor Frankl, which I think is quite good. It does a lot of physics kind of motivated stuff, and so I think that might be one of your best bets. Another book that I found that's good, but this is more from a mathematical side. Another book that I like is Spivak. It's very, very long. It's 5 books, but it's a really, really good reference, and it's pretty well written. I don't have a hard time following it, unlike a lot of textbooks. Some textbooks are poorly written. So Spivak's pretty good. But you could also pick up a textbook by, like, you could pick up a general relativity textbook by Sean Carroll, which teaches differential geometry with the goal of doing general relativity, which is a nice application. From Schrodinger Kitty with the $5, why upon reentry does the crew module not flip? The heat shield being the largest surface area falling first seems like it would flip tumble easily. That's a complex aerodynamic question. It's not clear to me that I mean, like, aerodynamics is often very counterintuitive. My guess is that the shape of the heat shield and the shape of the rest of the module is just more stable than the inverse. And they would have tested this in an air, like a wind tunnel, with like a small model. Yeah, it's not always the case that the bigger side is in the back, right? I mean, it is heavier, but that doesn't necessarily mean that it'll flip. Like, it's just a complicated system, and so like you can model it and see what the, depending on the shape and stuff like that, you will get different behaviors at different speeds. From Momo Gaipan with the $100, which is enormous. Thank you so much, Momo. What's the most mind-blowing thing you've studied in physics where the math or evidence points to something real, but the deeper why is still unanswered? Well, so look, and this is dissatisfying, but the reality is that physics rarely gives you a fundamental why, right? This is just not a feature that physics tends to do. Physics can give you sort of a how, or can give you a mathematical formula, but it doesn't really answer why. Now, probably the closest answer I have for the question that you asked is something like, why, and I made a video about this a while ago, it's really interesting. Why is it that we have laws of physics that goes inverse squares, right? Okay, it's a fine question. Like, why do they drop off with the square of the distance? Why not the cube of the distance? And it turns out it's because there's kind of two pieces. There's one, the fact that we live in 3 dimensions, and the other fact is that the laws of physics are gauge theories. They're gauge, or at least like electromagnetism is a gauge theory, and so it's a Yang-Mills gauge theory in particular. Now, why is it a Yang-Mills gauge theory? Well, it happens to, arguably, it's like one of the simplest mathematical forms that a force law can take. Why is it the simplest? We don't really have an answer to that. But it is really cool. And from Metal Roofing with the $10, hey doc, you're providing valuable service here. So many of us missed out on physics, so thank you. Do you believe that the universe is eternal? If so, how does entropy allow for that? Good question, and I appreciate the kind words. So I'm agnostic about whether the universe is eternal. So in my scientific research, one of the things that I'm currently working on is an eternal universe model, just because it's people have thought about like past finite universes for a long time. So I'm interested in seeing how we can make sense of what an eternal universe would look like. That said, I'm not agnostic about it. I don't have a strong belief one way or the other. I think that in principle both are possible. The question about entropy is, I'm more and more convinced that this is a misguided question. It's not your fault, but this assumption that like somehow entropy prevents us from having like a past eternal model, it's just not the case that we even have a good way to define the entropy of the universe. That's just not even like a sensible thing. And it's also not the case that even if we could define the entropy of the universe, it's not the case that it deterministically must always increase with time, right? Also, it's not even clear what time is. Like, how can we talk about time if we're talking about if we're doing like quantum gravity? That's not clear either. And so all of these questions about we can use the laws of physics to rule out a past eternal universe, we are far, far from being able to do that. But I appreciate the question. From Fleckboy sending 5 Dr. Blitz gift memberships, that's very much appreciated. Just as a quick word, if you don't know, a gift membership gets you access to 2 things at the moment. Actually, 3 things now. 1, it gets you access to emojis on YouTube, which is fun. There's a few of them. I need to add more, but there's a few of them. 2, you get access to my my personal debate notes, which I basically are a repository of links and arguments and counter arguments and sources and things like that for my debates. And 3, it now gets you access to send questions during the members only questions Ask a Physicist days, which will be every Wednesday roughly from 10:30 to noon. Today I have to shorten it a little bit because I have a meeting at 11. So you get access to some things. So Fleckboy, thank you for giving that to five new people. And if you are interested in supporting me that way, it's a cool way to do it. It's like $4 or $5 a month. All right, let's answer some more questions. What does, oh, okay, how does it do the thing that it does? Good question. What does the end of entropy look like, virtual particle? I don't know what that question means. What are some different forms that wave functions can take in quantum field theory? Different forms, that are they variable to the individual particles? So in quantum field theory, the particles are not the fundamental thing. The fields are the fundamental thing. And so what you have, the wave functions are not wave functions in as much as they are wave functionals. So you can have a superposition of different field configurations all kind of lying on top of each other. And so you could have like a superposition of one particle. You could have a field configuration that corresponds to one particle, or you can have a field configuration that corresponds to 8 particles, and they could be in a superposition of each other, for example. From Bacon Bush with the $20. Okay, so if light moves the same speed past my head regardless of my speed, but it's measured the same by anyone else regardless of their speed relative to me, why do I have a headache? Do you recommend Sean Carroll's books? Sean Carroll's books will probably do a good explanation of this, especially if you read the first one, The Biggest Ideas in the Universe, the first volume, which is Particles and, what is it called? It's not Quanta and Fields, it is Space, Time, and Motion. That book explains it pretty well. What is the center of SU3 and how does it act on quark representations? So in principle, the center is supposed to commute with everything. Okay, so let's back up. You're really quizzing me here, so I'll answer as best I can. So first we have a gauge group. A center is something that, so a gauge group is a mathematical object. It basically describes how things transform. A group is a mathematical object that describes how things transform. A gauge group is a particular kind of group. Now, like with rotations, if you do one rotation and then another rotation, it'll be different than if you do the second rotation first and then the first rotation second. You'll get a different outcome, which is to say that if you do different transformations in different orders, you'll get different answers. And so you can ask how much they fail to agree with each other when you swap the order of 2 transformations. That thing's called the commutator. So in general, for sufficiently small groups or sufficiently simple groups, the commutator is 0 between every pair of things. So that's an abelian group. However, most groups, probably like, you know, measure 1 groups, including SU3, which is a gauge group, is non-commutative. There are elements of this group. They're like mathematical objects that if you change their order, you get a different answer. And so what the center of a group does is it is the elements, it is the members of the group that commute with everything. Now the question is what was the question? The question was, what is the center of SU3 and how does it act on quark representations? So a quark representation is going to be a fundamental representation, or it's going to be one of the irreducible representations of the SU3 gauge group. So this is going to be a vector. It's going to be a, it's just going to be a vector in a certain dimensional space. I guess the fundamental representation for a quark is 3-dimensional. Now you're talking probably not about quantum chromodynamics. You're probably talking about, well, no, you might be talking about quantum chromodynamics here. Okay, so you have a vector. That vector is going to transform amongst the different. So what does the gauge group do? The gauge group tells you the different ways that you can write down different vectors, and so it gives you the dimensionality. So okay, so I guess the center doesn't. It's not really a meaningful question, at least not from a physics perspective, because you basically just have to choose. You have to choose like a way of writing down your representation, and the center's action will just depend on that. What's really important is the commutators, and what's really important is the ways that you can combine quark representations to get new representations. And the point is that somehow the action of the group on the quark representations has to respect the group action that you have without the representation theory, just like as a group itself. So that's probably not the answer you wanted, and it's probably not fully correct in that my understanding of the mathematics is correct, but the physical relevance to of the question I might be missing something key here. But that's the best I got for you. You're really making me go back because I haven't done any like quantum field theory with like Lie groups in 7 years. How's your diagnosis going? Any updates for those of us who care? I made an update video a while ago after my surgery. So go watch that. It'll be more informative than I can give you in a detail, but I'm fine. What's your job? Does physics open a lot of doors in the market? So I don't work for a company. I work for myself. I make my money doing, I make science content on TikTok and on YouTube and on Instagram. And I do, live streams. And so that's enough to pay to support myself. And it's enough to also support my research. So I work for myself. How does matter pop in and out of existence? One sec. It kind of does, kind of doesn't. What is true is that if you take two particles that are very, very high energy and you smash them together, you can get a lot more than two particles out. And so that would be an example of matter popping into existence. What's not true is if you just have a pure vacuum, it's not true that particles pop in and out, like actual particles pop in and out of existence. That's not true. Do you have a telescope? No, but I want one. What's my Discord? It's discord.gg/drblitz. All right, let's jump down to the bottom. Why can't you gauge classical dimensions? I'm not sure if that's really a well-posed question. You don't usually gauge dimensions. Why can't we see every string? Well, we don't know if string theory is true, so. What if we find something faster than light? Is there a possibility of something like that existing? We just don't know. Is this possible? Well, it's possible in the sense that it's not provably logically impossible, but it's impossible according to the laws of physics. So can you talk a little about your research, or are you keeping it close to your chest? So I'm not keeping it hidden or anonymous anymore. You can go look at my research by going to my website. It's blitz.phd. There's a research tab and you can take a look at all the papers that I've done and a summary of the research that I do. But I kind of have roughly roughly two modes that I'm working in lately. So I have kind of a pure mathematical mode where I'm working on conformal geometry, and then I have a kind of a pure physics mode where I'm working on model building for early universe models. So one of the projects I'm working on right now is trying to figure out a way that I can kind of have I'm trying to see if there's any sensible way that we can make sense of a universe that expands, contracts, and then in the next cycle expands and contracts but is smaller. And then in the next cycle, it's smaller and smaller and smaller. I'm trying to figure out, is that something that's possible? Can we make sense of this using standard physics without having to introduce something ad hoc? That's an interesting project for me, and I've spent a lot of time on it, and I haven't made a whole lot of progress on it. But yesterday I may have made some progress on it, and once that paper's published, or once that project's either done, if I've abandoned it, or if it ends up becoming a paper, I'll talk more on it when it's done. Can you explain what the Z-boson does? I've heard it carries momentum, but that's all, and I don't really understand that. Yeah, so the Z-boson is a lot like the photon. You can think of it like a fat photon. It connects particles with the same charges, and it can transfer momentum in the same way that a photon does. Is the expansion of the universe linear? We don't know. The acceleration seems to be constant, which would mean that in some sense, the velocity or the acceleration seems to be approaching a constant rather, which would mean that the velocity is somehow linear, but it's not really a velocity of a thing. It's more of the rate of change of the scale factor. Do you think the possibility of us harnessing creating antimatter will accelerate us in space exploration? Maybe, but we need to do a lot better than just hanging on to a few thousand atoms or a few thousand particles of antimatter for, say, 10 minutes. Any advice on studying math? Currently struggling with calculus. Look, so people ask me these kinds of questions a lot, and without having studied pedagogy, in a formal setting, I was a teacher obviously, but without having formally studied pedagogy, I don't actually know what the most efficient ways are, and I can't give you personal experience either because I didn't have that problem. So what I have heard that works though, what I've heard that's very effective is one, obviously doing practice problems, but that's not very satisfying. Finding physical intuition, so doing calculus with physics in mind can be helpful because it can help you build physical intuition for the mathematics you're doing. The other thing is approaching the same content from multiple different angles of learning. So read a textbook, watch a lecture, go onto YouTube and watch an animation, do some practice problems, a bunch of different modes of learning, and one of them might stick if you're struggling with certain concepts. Are you familiar with Professor Dave Explains? If so, do you like his content? I don't watch his content on the regular, so I can't really comment, but I'm familiar with him, yeah. What's your favorite thought experiment? My favorite thought experiment? Wigner's Room. So Wigner's Room is a thought experiment that is kind of used to debunk this idea that there is objective wave function collapse, or at least it's pushing at that. The idea is that, so suppose that there's Wigner and his friend. So Wigner's friend is in a completely isolated box. Think of, like, you know that show Dark Matter? He's in a completely isolated box, and he does a quantum experiment. So once he does the quantum experiment and he makes this measurement, from his perspective, from the friend's perspective, in the box, you know, the wave function, if objective wave function collapse is real, then the experiment that he does collapses the wave function. He gets one result. However, from Wigner's perspective, who's outside the box, the box has not yet had its wave function collapsed. What's happened now is that Wigner's friend is in a superposition with the stuff in the box, with whatever quantum experiment he did. So which is true? Is the guy inside the box, is he in a superposition or is he not? And that kind of like if wave function collapse is a real thing, then that's a question we have to answer. From Binary Ghost with the $10, I found what helped me immensely in study is preparing to teach the subject concept I was studying. Something about packaging things to explain to others really helps. Yes, that's really helpful, but that's not going to be helpful for somebody who still doesn't understand the concepts well enough to even pass a class. But yes, it is indeed true that teaching a class, you tend to learn it and grok it better after you've taught it than you did before. What amount of antimatter would it take to destroy the Earth's core, theoretically? You mean via the explosion or just to make it annihilate? Because if you mean just to make it annihilate, then you need the amount of antimatter equal to the amount of matter in the Earth's core. If you mean to just like from the explosion, we'd have to run some calculations. Mr. Boston, I didn't even see what your question was. Without using probabilistic models, what is the explanation of life, the universe, and everything? Oh, no, that wasn't Mr. Boston, that was somebody else. How do you solve Nikola Tesla current runaway? I have no idea what that is. Nikola Tesla wasn't a scientist, though, so. To what extent are pure mathematical theorems useful in physics research? To a certain extent, they are. Because they can give you no-go theorems, or no-go results, which means that you should have you should make no attempts to try to do XYZ thing, right? You should make no attempt to, you know, try to prove that this model does that if you've already proven mathematically that it's impossible given certain assumptions, right? Was there truly nothing before the Big Bang if matter can't be created or destroyed? That is not, the consensus view is not that there was nothing before the Big Bang. That's not the view. That's not like an agreed upon perspective of scientists. Also, matter can be created and destroyed. That's the trouble. Do you think parts of the universe are made of antimatter? If yes, they're very, very small parts. Why do electrons behave like a wave in the double slit experiment? Because everything is a wave, ultimately. Can you explain what quantum superposition is? Yeah, think of it as like a fundamental correlation between things. So if you have, superposition, not entanglement. Yeah, superposition is fairly easy to describe. Once you recognize that everything is, all matter is really waves, then we can talk about superposition, because superposition is just what happens when you have two different waves kind of in the same place at the same time. Imagine playing two different strings on a guitar at the same time, plucking two different strings. The sound waves that are produced will be in a superposition of those two different waves. That just means that they're added together. And because matter, particles, all of this stuff, these are all waves, those waves can be in superposition. They can add on top of each other. From Binary Ghost with the $5, again, much appreciated. That's right, Tesla wasn't a scientist, he was an engineer. He belongs to us. You science folk, keep your grubby hands off him. True. He was an engineer, he was an inventor, he wasn't a scientist. Can you explain the Alcubierre drive? Yeah, the idea is fairly straightforward. I mean, insofar as any GR stuff is straightforward. So we know that somehow, we know that space can expand, which drives things apart. And in principle, space can compress, which would pull things together. So what the Alcubierre drive is trying to do, or what it basically does, is it makes space expand behind you and compress in front of you, and that drives you forward. And because the amount of space-time curvature is basically like there's no like limit for how much maximum space-time curvature you can have. You can go arbitrarily fast. The trouble is making the space expand in front of you seems to require negative energy, which we don't have access to. Or negative mass, I should say. Can you explain Lagrangian mechanics? Lagrangian mechanics, Hamiltonian mechanics, and Newtonian mechanics are all equivalent, or at least equivalent in some regards. Lagrangian mechanics is basically taking the, it's kind of like a global view of the mechanical system, rather than thinking about the way that the world is now and then asking what it'll be in the future. It's like, given two endpoints, what's the trajectory that the system will take between those two endpoints? Lagrangian mechanics gives a solid answer for that. And the end result is that you end up with equations of motion that tell you how to evolve step by step, because that's telling you how to connect point A to point B. From Bacon and Bush with the $5, how to explain the atom's electron cloud? Is it stuff everywhere or a thing that can be anywhere? That depends on your preferred interpretation of quantum mechanics. My view is that it's, in some sense, stuff everywhere. It is, you know, the electron field, or the electron cloud is the electron. So I take it that the electron is just kind of smeared out over the entire, over however far the cloud is. And in some sense, that means that the electron cloud is infinitely large, but we kind of cut it off where like it starts being negligible. What's the topology of the universe? We don't know. This is an open question. Element 115 might work. Element 115 is not a special element. It's not particularly stable. It's not particularly useful. Physicists don't know what electron looks like. You can't see it. They've never seen it. Hypothetically, it doesn't exist. Hypothetically, it does. I mean, it's not true that hypothetically it doesn't exist. Electrons do exist. We can measure them directly. And look, if you think that electrons don't exist, then feel free to go stick your hand into an electron-positron, or like an electron-positron beam or something like that, right? You'll find out awfully quickly that it does exist. From Angelus with the £5, do you think that Star Trek Warp Drive's pre-Alcubierre version, where masses move to a higher lower dimension, could ever be a possibility? I don't think so. I mean, it's science fiction, right? Like, they had to make up something to make it work. I don't think that their version is the kind of thing that's going to work in real life. What do you do with transcendental numbers like pi? Do they not allude to the fact that reality is just infinitely more complex and vaster than we could ever imagine or hope to understand? Transcendental numbers aren't infinitely complex, right? Transcendental numbers are finite. Doubting Thomas with the $10. Hello, fellow PhD here, working on a Green's function approach to solve a non-perturbative QED problem. Suggestion on how to avoid accidentally inserting mean field theory assumptions. Happy to chat one day. Oh, well, look, if you have a PhD and you're doing quantum field theory, and especially you're doing non-perturbative QED stuff, that's above my pay grade. I don't do quantum field theory. That's not my area of expertise. I do GR. I do differential geometry. I guess you'd have to be a little bit more specific, and I could maybe, we could maybe brainstorm something, but like you are as much an expert on that as I am. So I got nothing for you, but I do appreciate the donation. From Fleckboy with the $2, that's a lie. Element 115 creates zombies. Ah, yes, Element 115 creating zombies, famously. From Fleckboy and from Binary Ghost with the $5, in Star Trek, they often talk about subspace. Is there a physics concept behind this? If so, what exactly is subspace? The show does a lot with it. No, as far as I know, there's nothing that corresponds to subspace in the real world. My technology is 500 years above everyone else's. That's crazy. That's a crazy thing to say. Do you think humans can create wormholes to travel to distant solar systems, or is that impossible? Look, so there is a problem with stabilizing a wormhole. You would need, so generally this seems to be, it's not quite proven, but this seems to be a no-go conjecture that if you wanted to create some sort of space-time feature that would let you get from point A to point B faster than light, it would always require negative mass. That seems to always be the case. So like if you want to make an Alcubierre drive, you need negative mass. If you want to stabilize a wormhole, you need negative mass. If you want to make a wormhole large, you need negative mass. So it seems like there's nothing that you can do. So no, I don't think it'll be possible. From Clibs with the $5, in your opinion, what's the most plausible form of FTL travel presented in sci-fi? Probably none of them. Well, yeah, I mean, the thing is they all seem to equally require some kind of like negative mass, which we don't seem to have access to. It seems to be made up, not a real thing. From the Turk with the $2, why don't clouds keep going up? Density gradient. Why don't, are you asking why clouds don't fly higher and higher? Well, yeah, they're buoyant, right? They get to the point of neutral buoyancy, and then that's where they float. The gravity pulling down and the buoyant force pushing up are equal. Skip down to the bottom so I didn't miss any. What is gravity? Gravity is the phenomenon that we observe of things falling, of mass attracting other mass. Is the Twitch chat not coming through? The Twitch chat might not be coming through. One sec. Okay. What are your thoughts on spirituality and its relation to physics? I'm not particularly interested in that stuff. I'm not sure it's really related to that stuff either. From the Lowly with the $10, could gravitational waves from black hole collisions help explain the universe expanding faster than light, similar to the Alcubierre drive concept? Gravitational waves don't produce this kind of... gravitational waves are more of compression along different axes. There's no kind of expansion, right? Well, okay, I guess that there is in principle expansion because it's a wave, but that's neither here nor there. They don't... The answer is no. But also, the universe isn't expanding faster than light. The universe expansion doesn't have a speed. It has a rate. It's not distance over time. It has an amount of time it takes to double in size, basically. Now, what is true is that because of the universe's expansion, there are objects in the universe whose distance to us is growing faster than the speed of light. But the universe itself is not expanding at a speed. It's kind of a category error as far as questions are concerned. But yeah, gravitational waves generally are not going to be able to accelerate things faster than light. They just have the wrong geometry. Are you spiritual? No, I'm not. From Hosenhofen with the $5, if you could have a sci-fi ship and it did its sci-fi things, would you pick it? What would you pick if you could? Oh, this is a good question, actually. So I have to admit, I'm not very broad in the sci-fi that I like. I like Star Trek. That's like the extent of the sci-fi. Okay, I mean, there's other sci-fi that I like, but that's like the main sci-fi that I like. That said, the Enterprise, maybe the Enterprise D, the Enterprise E or something like this, or maybe the Galileo, which was a time ship, those would be cool. Can't we get negative mass from gravity if dark energy is a gravity geometry phenomenon? Well, you would need it to be a non-geometric phenomenon, right? Because then there's nothing. If it's a merely geometric phenomenon, then you can't get anything from it. It's just a feature of spacetime. If you have like a phantom field, though, then maybe you can. You'd somehow need to be able to harness that phantom field, and then sure. But I'm very skeptical that that's the case. Is the expansion of the universe infinite, or does it have limits? Will it reach a maximum threshold? Will it implode and start again? Again, the question doesn't seem well posed. The universe is not something with edges, and the edges are getting further away. Right? The universe, as far as we can tell, doesn't have edges. Whether that means that it doesn't have edges like the surface of the Earth doesn't have edges, so the surface of the Earth is finite, but there are no edges. You can walk in any direction forever, and you'll never reach an edge. Or if the universe itself is infinite, both of those things are compatible with the universe that's expanding. The expansion is more of like a local thing, namely that like the mean distance between two non-gravitationally bound things is growing with time. But as it currently stands, we don't really have any reason to think that the universe is going to implode and start again. Now, that's not to say that it's ruled out, but we don't know that it's ruled in. This man would have you think there's a black hole at the center of the universe that is sucking everything inwards, but the opposite is true. It is forever expanding. I would never say there's a black hole at the center of the universe that is sucking everything inwards. I don't even think that there is a center of the universe. But cool straw man, I guess. How many hobbies do you have? Fewer than I would like. I spend a lot of time doing social media content creation, science communication, live streams. I spend a lot of time on that. And the time that I don't spend with that, I'm usually just hanging out with my family. So what's your thoughts on time travel, and is time travel to the past possible? I take the position that either time travel to the past is impossible, or literally our universe is a time machine, meaning that it will loop back on itself at some point if you wait long enough. One of those two, I think that one of those two things is true. I don't think that you can like locally go back in time without passing all the way around the universe first. From Brain Segfault with the $10, what are the limits of AI statistical inference in understanding the universe, and do most physicists agree on the boundaries of its usefulness? I have no idea what the limits are. I don't think anybody knows what the limits are. And I have no idea what most physicists agree on or don't agree on with regards to AI at all. This is a brand new world, right? Like, who knows how useful AI will end up being? I feel bad because people ask me these questions that like nobody has the answer to, and they send them with super chats. So I feel like I should give an answer, but if nobody has the answer, then it feels like it's wasted money. From Doubting Thomas with $5. So if you are a GR guy, what do you think of Penrose's gravitational collapse model? What's the best way to reach out to chat? Would be fun if recorded. So are you talking about the gravitational collapse model, like OR? I think that that's pretty far-fetched. So if you're talking about like the collapse model of like quantum, you know, solving the quantum interpretation problem, yeah, I think that's pretty far-fetched. I don't buy it. I think that gravity's too weak for that to happen. But if you're talking about something else, then that's not what then I'm not familiar with it. I mean, you could be talking about like CCC, which is something that is also pretty far-fetched, but is a good idea. If you're talking about just like Penrose's idea about like his singularity theorems, those are brilliant. What's the best way to reach out to chat? Just join my Discord server, and I'm around sometimes. Now, if you want to have a debate on like one of the topics that I do debates on for like a recorded thing, then you can call in on those days. But generally speaking, I don't really have enough time typically to like do like recorded sit down just conversations. Like if there's like a show that you want me to be on, like we can talk about it, but that's what the website's for. If you go to contact me, there's a drop down where you can say like speaking engagements or something, and you can send me an email there. From Angelus with the £10, if objects approach the event horizon of a black hole, it would appear to stop, not disappear to an observer, but wouldn't redshift of the light bouncing off the object make it appear to disappear? Make it seem to disappear. Yeah. So from an outside observer's perspective, you never actually get into the black hole. But that's not because you didn't get into the black hole. It's just because the light from you can keep going. The light from you will make it off to future infinity, or future time like infinity. So this is to say, yes, they will see you there forever, but that's just because your image is basically frozen, and the photons will keep being emitted, and yes, they will be redshifted and appear to disappear. But you actually would pass through. That is true. It is true that you would actually get through the black hole if you were the person falling. You getting bored debating the flat earthers? Not really. From Demtra with the $5, is it fair to compare the expanding universe like an expanding balloon? Yes, so long as you recognize that it's one dimension down. So the surface of the balloon is two-dimensional. And our universe is three-dimensional. So you would have to recognize that this is a dimensional reduction in order to get a better intuition for it. But what isn't true is that even if our universe does have that kind of geometry, it does not therefore imply that our universe is three-dimensionally spatially embedded in a four-dimensional universe that has like a center. That does not follow. But thank you guys for the questions. Should people be worried about vacuum decay? No, because there's nothing that you can do about it. Worry doesn't serve any purpose if there's nothing you can do about it. Let's say two spacecraft travel behind each other at basically light speed. The latter flashes its headlights as the first one able to see it. Are they flashing their headlights? Oh, the latter flashes. Yeah, eventually, yeah. Cat get your nose? No, this is an injury from a surgery. How dare you ask that? I'm so offended and so hurt. I'm kidding. But no, it's an injury from a surgery. It's healing. How's momentum described in modern physics? Since for photons, the relativistic equation is E equals PC, how can a photon have momentum without mass? Well, so the momentum of a photon is just related to its wavelength, or it's related to its frequency. The way that you define the momentum of a system, generally speaking, like it is involves, let me back up. So you have some physical system, you describe it with something called the Lagrangian, or you can describe it with a Hamiltonian, but let's just talk about the Lagrangian. If the Lagrangian has certain properties, that means that there's going to be certain conserved quantities. Now, energy is a conserved quantity, momentum is a conserved quantity, typically angular momentum is a conserved quantity. All of these are things that don't change unless something external happens, right? And once you have that Lagrangian, there's basically a test that you can run on it to see if it has a conserved energy, if it has a conserved momentum, if it has a conserved angular momentum, and so on. Not all systems do, but some systems do, the nice ones do. And so once you've checked whether there is a conserved momentum, which, for example, for the electromagnetic field, which is what photons basically are describing, for the electromagnetic field, there is a conserved momentum, then there's a formula that you can plug in to get the momentum, whatever the momentum is, for that system. And so that's how you get it. That's how you define momentum in modern physics. You start with a Lagrangian, and then you find the conserved quantity associated with spatial translations, and that conserved quantity we just call momentum. Are white holes possible to exist, or just a mathematical theory? If white holes do exist, they're not like the white holes that you might think of from science fiction, and they are very, very temporary, and perhaps very, very small as well. Let's jump down to the bottom. I'm a bit behind. Sorry, everybody. Do you have a favorite analysis text that isn't Rudin? I don't have any favorite analysis texts because I don't do analysis because analysis sucks. Is there any quantity in physics that is not conserved? Yeah, temperature. How does it work that the area past the event horizon of a large black hole are less dense than air? Well, oh, you mean the area within the event horizon. The density of a black hole decreases as the mass increases. That's just a feature of black holes, because the event horizon grows with the mass. So if you double the event horizon, or if you double the mass, then the event horizon doubles in size. Whereas the mass. Sorry, hold on. If you double the mass, you double the size of the event horizon. But if you double the mass, but if you double the size of the event horizon, then the density goes down by the square of the mass, because the mass goes up linearly, but the volume goes down as the cube of the radius, and the cube of the radius goes with the cube of the mass. So it's just because the density decreases as mass increases for a black hole. From binary ghosts with the $10, sorry, there used to be a center middle point to the universe when it was flat, like paper. When it was crumpled up, that middle is lost. The expansion is the uncrumpling of the paper ball universe. There is so much wrong here. I think that this is a troll, right? I think that this is like a meme. So there's not a center of the universe as far as anybody can tell. From Angel Ramirez with the $2, can you look at my comment if I can find it? Still too poor for a super chat. Would you consider having guests on your Ask a Physicist streams? Yes, I mentioned this. We're going to bring up guests shortly. But it's going to be restricted. At least I'm going to try to restrict it. I don't know how. Restricted for members and subscribers, members on YouTube and super fans, or whatever they're called, on TikTok. I need to figure out a way to filter that because I don't have a way to do that yet. But the intent is this is a way to encourage people to become members and, give me $4 or $5 a month or something like this, right? But yes, I will be bringing on guests in about 25 minutes. What tech do you think is sure despite seeming unthinkable now? I have no idea what that means. I don't know what that question means. Is your health better? Yeah, I'm getting better. Just ask if they're cool or not. Good point. I should just do that. Why can't I poke the moon with a long stick and it be faster than light? Well, whenever you touch something, the response on the other end is not instantaneous, right? The response on the other end, it takes time for your poke to kind of transmit through the rod. And that rate at which it transmits through the rod is the speed of sound in the material. And this kind of makes sense, right? Like if you tap a rod, for example, there's like a compression wave that travels through the rod, and that's moving at the speed of sound. So pushing it would be the same as a compression wave. It just doesn't have a back end. So it'll actually move significantly slower than the speed of light. How do we know that the wave function is a proper description of the quantum system's evolution if it collapses as soon as we make a measurement? Because it makes really, really good predictions. That's what it boils down to. What if the universe is expanding because due to the energy that lies in the boundary? What if horses, hand grenades, something? I don't know. What's your opinion on how the universe will end? I don't have one. Can we read your PhD dissertation? I don't have it uploaded anywhere. I'm sure it's available somewhere, like in on one of these like PhD repository websites. But what you can do is you can go look up at like some of my first papers, and I basically glued those papers together and made a PhD out of them. Is the physics in the show The Expanse truly accurate for space travel? I haven't really watched it, so I can't comment. What if the universe expands due to expansion of dark matter? I don't even know what that means. So dark matter is whatever dark matter is. It's some sort of stuff that moves like normal stuff does. It's just dark. We can't see it. The name for the thing that is causing the accelerated expansion of our universe is called dark energy. Question about the new CMS quark compositeness result. They probed quarks down to 10 to the minus 20 meters and found no evidence of substructure preons. Okay, that sounds... I'm not familiar with this result, by the way, so like I might not have any comment on it. Look, so you guys might think that I spend all my time reading science news. I don't. When I'm not live streaming, when I'm not writing scripts for videos, I'm actually just working on my own physics projects, like my own research, right? You'd be surprised how little physicists, especially, I don't know about other fields, but physicists actually spend reading about every other experiment and every other result that pops up that is not directly within their own particular area of research, right? Doesn't Hubble's law prove that the universe is finite? No. Hope my nose is healing well. It seems to be getting better, but what are your thoughts on why the cosmological constant is so finely tuned? I don't think it is finely tuned. In fact, I don't even think the cosmological constant that we measure is the true value of the cosmological constant. The value of the cosmological constant could be 0, it could be negative, and we wouldn't know currently. How do photons carry momentum while not having mass? Because momentum is not intrinsically related to mass. That's only true for non-relativistic massive particles. Since you're 8'4", does time run differently at your height while standing up? Yes, my head ages slightly slower than sorry, my feet age slightly slower than my head does. Is your project about dark energy? It involves it, but what's your current area of research? So I have kind of two branches. I have one area that's kind of, I'm looking into, early universe models and kind of like quantum cosmology stuff. And then the other branch is more mathematical. I'm interested in like conformal geometry. New here, what happened to your nose? I had surgery. They taped something to my nose. When they took the tape off, it took some of my skin off too. Tips for applying for a university's physics program. For an undergrad, honestly, just get good grades. For an undergrad, get good grades, have as many extracurriculars as you can, because God knows that's what's required these days. For a grad program, it's a lot more competitive nowadays than it was when I was in school, which is hard. You need publications, apparently, which sucks, because how are you supposed to get publications as an undergrad, right? You don't need it, but it's recommended. Thanks for the previous answer. Would it be correct to assume that a quantum entity's momentum is directly related to how the system's Lagrangian changes with change in velocity? A quantum entity's momentum? So defining the momentum of a quantum entity is much different than defining it classically. So not quite. What is true is that what is true is that classically well, okay, you can't even say that it's with, You have two canonical variables, basically. And so you're going to have a variable, and you have your canonical position, which is not necessarily position, and then its rate of change, which is not necessarily velocity. Now, the derivative of the Lagrangian, with respect to the velocity variable, that will give you your momentum, so long as there's no other time. Actually, hold on, I want to make sure that I'm saying the right thing. Yeah, so long as there's no spatial dependence of any of your quantities in your Lagrangian. Explicit spatial dependence, I should say. I would have to write down the other Lagrange equations and just actually do this, but your thoughts on the 3D render of the universes recently? I have no idea what that's referring to. I'm writing a paper, but I've put 3 things to you. But I haven't had any responses. Would love your feedback. I don't do paper reviews. I don't do, it's just not what I do. Like if somebody's like if a journal asks me to review a paper for them, I consider it. If another scientist, another physicist wants to collaborate with me on something, I will, we can talk about it. But if it's just some random person, I'm sorry, I don't have the time to review every paper that people are writing. Saw your big crunch video about the paper you co-authored. How much matter could reverse the expansion? Maybe just 1 electron. So in that context, we were assuming the universe was homogeneous, and so it's just that the matter density was very, very low. So you can't really talk about single particles there because we're not talking about that would make the universe inhomogeneous. So how do I convince my religious friend that space is real? You have a deeper problem if they don't think that space is real. Are we at the end of science or physics? If not, speculate on the science of tomorrow. That seems impossible now. So we're not at the end of science or physics. I could speculate all day. You know, in 100 years, maybe we'll have a theory of everything. But definitely we're not at the end of science or physics. There's just no reason to think that. Is the inside of a black hole devoid of time? Could a black hole be considered anti-time? No, there's time inside a black hole. At least we have every reason to think that there is. Yeah, I mean, the reality is that a lot of people ask me, hey, will you take a look at this paper that I'm writing? I don't know how to do the mathematics, but I have this idea. And I get probably half a dozen of those a week. It's just not practical for me to go through all of them because inevitably the answer is going to be, it's not a good idea, it doesn't work. And I don't like giving bad news either, so I just don't, I have this blanket policy, I just don't do that. From Hercules with $5, can you throw some realistic sounding physics word for a futuristic sounding gravity bending technology? Would love your help grounding some hard sci-fi. I can just, you want technobabble? I don't know, an inverted Casimir generator to produce tachyonic field excitations or tachyonic Higgs field excitations. I don't know, those are some good words. And these tachyonic Higgs excitations invert the Weyl tensor. I don't know, there's more words. Invert is always a good one, polarity is a good one. You learn these a lot from Star Trek, right? But good luck, good luck. All right, I gotta hydrate. If two photons are moving at the speed of light towards each other based on relativity, isn't it equivalent to one photon being stationary and one photon moving at 2x the speed of light towards it? No, it's not. Also, people talk about this is just a it's not at you, Darkwitch, this isn't your fault. People talk about photons way more than they should. People should be talking about electromagnetic waves. Photons are not little particles, right? They're not like little billiard balls moving. They're waves. Now, It's just not the case that there's a valid reference frame where one photon is stationary, or where one electromagnetic wave is stationary and the other one's moving at 2x the speed of light. That's not a valid frame of reference, because electromagnetic waves always move at the speed of light in every frame of reference, every valid frame of reference. So are black holes an object that is so massive that light can't escape, or is it like anti-gravity? No, it's like the former. They're like very, very strong gravity. Who's the one you call Dr. Feelgood? No. No. Do you think that currently atheism is as harmful as a belief? Is as harmful a belief as theism? I don't know. I don't really have any data on that one way or the other. For context, the non-perturbative project will modernize Mach's principle right up your alley. You shouldn't need QED, non-perturbative QED, in order to talk about Mach's principle. That should be like a strictly GR thing, so I have no idea what you're doing there. But if you want to DM me, we can talk. Like, join my Discord, feel free to DM me. It could be interesting if it's up my alley. Can you give a comprehensive breakdown of the DESI research? So I haven't followed up with it. I know that there was a recent release, I don't know, like a month ago or something. But I haven't looked at that yet, and I haven't looked at the follow-ups. My understanding is that they're basically looking at, there are these things called baryon acoustic oscillations. Baryon acoustic oscillations are essentially kind of the imprints of sound waves in the very early universe. And the size of those baryon acoustic oscillations at different distances gives us kind of a history of how the universe has expanded. And so by taking the average distance between pairs of galaxies, like by basically taking a huge survey of galaxies and then finding the average or the distances between those galaxies, we can get some sort of understanding as to how the universe has expanded over time. And one of the tantalizing conclusions is that it seems like the universe is, the data that we have is compatible, at least it was last year. I don't know if the new data rules this out, but the data that we had was compatible with a universe that doesn't have a cosmological constant, that has some other feature. And somebody asked, can you show your degree? Here it is. Here's the degree. Put this back in my folder of documents. I don't have this hanging up because I'm in my living situation never feels permanent, always feels temporary. So it's just in a folder somewhere. Do we know why energy is conserved, or is it from experimentation, or is there mathematical proof? We do know why energy is conserved in the cases where energy is conserved. This follows from Noether's theorem, which was proved in 1917 or something like this. I have a paper on a modified Maxwell modified Einstein equation and Kuramoto synchronization. Look, if you are a physicist and this wasn't generated using AI, then, and you want to work on stuff that I've worked on, then DM me and we can talk. DM me on Discord is probably the easiest way. If you are not a physicist or a mathematician, or if your stuff is generated by AI, then don't. I just started my path to becoming a physicist at age 30. Am I too late to the stage? You're not too late, but you are later, which is, there's like not something intrinsically wrong with that, but just recognize that, you know, there are younger people who, actually, I don't even know if there's an age bias when hiring. So yeah, I don't think you are. Can we actually know how much mass can a black hole take in? Black holes don't have a maximum size. They do have a maximum rate at which things can fall into them, at least like in the normal accretion mode, where you have like gas being, or when you have like something falling towards a black hole, if it's not going straight in, it will like basically be torn apart. And when it's torn apart, there is a maximum rate at which it can kind of like, there's a maximum rate at which things can fall in from that torn apart, the shredded stuff that was trying to get in. Are black holes' surface hot or cold? They don't really have surfaces. Can you explain with BS in engineering go the path you have gone and what type of engineering do the path you have gone and what type of engineering fit for that? Well, I mean, you're going to need a physics degree, right? That's the path that I went down. I have a physics degree, and so I was able to apply successfully to get into physics grad school. The thing is that grad school is competitive. And so unless you have the necessary knowledge and you can prove it by having taken the classes or something else, then physics undergrads are going to outcompete you for physics grad programs. Did AI have any positive impact on your field of study? Probably more of a negative impact than a positive impact, if only because people think that they're solving physics problems now, like lay people are think that they're solving physics problems, but really AI is just being too nice. That said, I do use AI as like a rubber ducky in my research. Why did the early universe have such a low entropy? Well, if we grant that it had low entropy, I don't know. But it's not even clear that it's true that it had low entropy. ChatGPT is good for laymen for physics explanations, for it will keep explaining from basics. ChatGPT is only good for explaining things that you can find in a textbook. Is there a quantifiable way to measure the total energy of the universe? Possibly not. Can objects orbit a black hole? They absolutely can. Is the couch equation a math problem or a physics problem? It's a math problem. What is rubber duckying? It's where you basically like talk to something just to kind of like get your ideas out. Like programmers used to do this, where they'd have like a rubber ducky on their desk and they would just talk to it to like walk through their, you know, their algorithm or whatever. Can I use electromagnets to slow down bolts that come near you? I mean, yeah, but it's not going to stop you from getting hit and dying. Why can we not measure it? It might not even be well defined, right? There might not, like, it's, in fact, like we know that at least in the usual sense, there's not a well-defined notion of energy for our universe, because our universe is dynamical, and a dynamical universe just by definition, kind of, not by definition, well, yeah, yes, by definition of what energy is, a dynamical universe doesn't have a well-defined energy. Do you believe Bob Lazar? No. No one should. Did the universe have zero entropy at the moment of creation? It's not even clear that the universe was created. Is there a name for the similarities between viewing atoms and viewing space, galaxies, the universe? Well, they're not really similar at all. Maybe seeing patterns where there are none? Other than the speed of light, are there other similar constraints on physical reality? Would temperature be an example or no? Not really. What is true is that the constants of the universe, whatever the constants are, they seem to be constant in all frames of reference. Any ideas on why space began to expand during the Big Bang? Nope. We have no data that explains why that's the case. No definitive data anyway. From PX's double D, I'm not with the $10. I'm not understanding spatially what's happening in the delayed choice quantum eraser. Explain like I'm an interested layman. So first you have to just grant that quantum entanglement is the thing. So you have two entangled things, one thing lands on the detector, and then later another thing gets detected by something else. So when the particle, assuming that just assume regular wave function collapse, when the particle takes the short distance and gets to the detector and hits the detector, the place where it ends up being detected is going to determine the probabilities of the particle being detected by one pair of detectors or by the other pair of detectors. That's all that's happening. We say it's delayed choice because if you filter out the data on the close detector based off of the data that you saw on the far detector, you can filter it in a way that it makes it look like it appears like two blobs, or it can look like it's interfering. But that's a post-selection filtering effect. This is not, you're not changing what actually happened on the screen. What actually happened on the screen will always be that there's two blobs. You'll never get an interference pattern on the screen when you like actually take all of the data. It's just if you filter out some of the data based off of what you detect later, then you can filter out some of the data so that what's left behind is an interference pattern. So that's like a computational filtering thing that you do later. What if dark energy is just gravity propagating through a fifth space-time dimension? Gravity is attractive, so it wouldn't at least like standard gravity is attractive, so it wouldn't really work. Somehow we need something to be repulsive in some sense. From Nathaniel Perrin with the $5, I have heard that some things like radioactive decay are uncaused. How could we know that, or do we just not know the cause? Well, okay, so there's kind of two things happening here. The point is we have a standard model of quantum mechanics, and given that standard model of quantum mechanics is true, it is just the case that there is no kind of temporal cause for the radioactive decay happening when it happens. That's just the case. Now, if quantum mechanics is not true, well then sure, I guess anything goes out the window, anything goes. But the data that we have, this is an inductive argument, the data that we have indicates that quantum mechanics is true. So there's just like, that's just what the data is. Now, could it be the case that like, that we're wrong about everything in physics? I guess, but you know, you'd have to make a compelling argument that shows that that's the case. From Saint Diluted with the $5, from @EnoughData. Can you explain what actually happens to light when it seemingly changes speed as it passes through a medium? Yes, I have a video on this. There's kind of a few different ways to understand this, but one of the ways that I like to understand it is that it stops being light, right? It just stops being light. It becomes, so what light is it is electromagnetic waves propagating freely, but electromagnetic waves do not propagate freely when they're in a medium because there are charges around. And so what's really happening is that you have an electromagnetic wave, and that electromagnetic wave interacts with the, you know, the electrons in the stuff that it's moving through. And those electrons then vibrate in a particular way. And that vibration affects the electromagnetic waves. The electromagnetic wave affects the electrons. The electrons affect the electromagnetic waves. And so that joint propagation, the electromagnetic wave and the vibration of the electrons, those things together travel through the medium at some speed. And there's no reason why that has to travel at the speed of light, because the electromagnetic wave, or the electrons, are changing the electromagnetic wave from doing what it would normally do. And from Stephen Smart with the €5, from the smallest to the biggest scale of the universe, are humans roughly in the middle? No, I think that we're closer in scale to the size of the observable universe than we are to the Planck scale. And from Sterling with the $5, do we know if absolute zero exists in the universe, like the furthest edges or something? And do we have theories on what happens to matter at absolute zero, presumably? So no, we think that absolute zero doesn't exist. It probably can't exist. This is the third law of thermodynamics. There's also not an edge of our universe, so it's not really like, you know, even if absolute zero could exist, it wouldn't be at the edges because there isn't an edge. But yeah, so the point is that you can't really get to absolute zero, but we can model systems that are at absolute zero anyway. They're just non-physical. They would just be approximations of very, very cold systems. And they don't really behave much differently from things that are otherwise very, very cold. It requires infinite energy to get to absolute zero, so it's impossible. I don't think it requires infinite energy, but it requires infinite steps. The third law of thermodynamics is something like there are no finite number of, or there is no process through a finite number, or there's no process by which you can do a finite number of steps of that process, or some combination of that process and other processes, to bring a system that's not at absolute zero to absolute zero. Is there an absolute highest temperature? Not really. There is a temperature, there's like a Planck temperature, but that's not like the highest temperature. It's just where like quantum gravity stuff is probably going to be relevant. Could a world model be built from a crystal radio fed into a neural network utilizing Hodge decomposition? I have no idea what that means. Like, I know what Hodge decomposition is. I don't know what the rest of it has to do with that, though. Will studying physics help me get a girlfriend? Probably not. Famously, probably not. What exactly is dark matter? We don't know. It's something that looks like it behaves like normal matter, but it doesn't interact with light at all. Hodge theory is a branch of mathematics. It's a branch of, like, you can say like it's algebraic. It's related, or it's pretty fundamental when you're doing differential geometry. I don't want to go much deeper than that, though. Like, the Hodge decomposition is the statement that, or a Hodge decomposition is a statement that you break down a form into a closed form, a co-closed form, and then a harmonic form. Like, that's what the Hodge decomposition is, if I remember correctly. All right, so it's 10 o'clock. So I'm going to shift over. Everybody can stick around, but what is going to happen is that all of a sudden, the only people who will be able to send messages now are going to be the people who are subscribers. So I just have to turn that on really quick. Subscribers, or super fans, whatever the correct phrase is. This should hopefully encourage you to support the live stream. And if not, you can still stick around. But, hopefully it'll encourage you to do that. Now, I need to figure out how to do this on TikTok. I know there's a way to do it. I just need to figure it out. How do I do this? Settings, maybe? No? Invite, history, introduction, manage guests. No. I know there's a way to do this on TikTok. I know there's a way to do it when you start the TikTok live stream, but I don't know if there's a way to do it while the TikTok live stream is going. Anybody know? Hold on, we can figure this out. Yeah, I'm using TikTok Live Studio. Absolutely. Settings, navigates settings. No, it's not what I want. Oh, I know what to do. Go to live chat, and then I go to, this is, okay, so show messages only from, so show messages for, no, we'll figure this out. Fans? No. Why is this not a... That won't do it. We'll figure this out. We'll figure this out, y'all. Settings, navigates the subscription setting. Close. We almost got there. Almost got there. It's definitely something that you can do live. But I just don't remember how, because I did it last time. Settings, moderation. So I go to settings. Settings. Where's the moderation settings? Ah, here we go. Oh. Why can't I change this? Oh, I actually don't have this. I actually don't have this set up. I'm gonna close the live and then restart it really quick. Because I think that's what I have to do. But we'll be back. Be back in 5 seconds. Anybody can listen. It's just, super fans will be able to watch. This is always a pain. I'm sorry, guys. And then I go here. No, it's here. I go here. Then I go to fan club zone. And then I do that. And then I go live. Bada bing, bada boom. We got it. We did it. We did it. All right. Now we can go back to answering questions, y'all. Okay. Sorry. And we're also going to be bringing up guests for the next 40 minutes or so, 50 minutes. I have a meeting in just under an hour, so I will just end the live stream before the meeting is over. Sorry, let me answer some questions. Do you think I should go to China for my undergrad? You could if you speak Mandarin. That will make it easier. I wouldn't suggest it otherwise. Is it more logical to conclude a finite universe or an infinite and eternal one? I don't think that one is more logical than the other. Yeah, we're back. We're back. Mod only. What's mod only? Oh, wait, hold on. Have I been missing? Oh, okay. Well, that's a Twitch thing that I'll have to change, but we'll worry about that later. What's the one thing in physics that keeps you up at night? I just want to know how it all works. I want to know the full answer, right? I don't know how this encourages people to subscribe and instead pisses people off. Well, look, I answered questions from everybody for an hour and 15 minutes. Anybody can watch, but I mean, there has to be perks for members, right? I'm not gonna lock the video behind, lock the live stream that way, but I think I've seen it done live too. How do you reconcile quantum mechanics with general relativity? In a complete quantum theory, complete theory, quantum gravity. Yeah, I can't. Nobody can. Nobody knows how. We are back. Welcome, welcome, everybody. Hope you didn't toggle what I think you did. Changing to members only mode with only 120 viewers on YouTube is an interesting choice. Fewer viewers now. Everybody can watch. It's always that dang TikTok. Indeed. Unhide the link. The link is still fine. I'm still taking guests. Oh, unhide the link. Yes, yes, yes. Unhide the link. I'm sorry. Not hide it. Yes. Okay. Still taking guests. So yeah, if you want to hop in, you can either join via TikTok or you can join via Discord if you're watching on YouTube. And I'm happy to answer questions from people that are, want, 5-10 minutes to ask a question or ask more than one question. Sterling, welcome to the party. Thank you for becoming a member. It's much appreciated. Yeah, you can still chat on Discord. You can join the Discord and you can chat, but I don't typically read the Discord questions while I'm there because it just takes too long. And I have too many things going at the same time. All right, let's bring up a guest. Zeno, how's it going?
Hey, what's up, Blitz? Quick question. So,
Yeah.
I have this philosopher. He's at the University of Texas. And he's basically Robert Coons, I think is his name. But basically, his whole new thing has been he's kind of an Aristotelian. He's a Thomist, and he's posited that quantum mechanics can kind of be, I guess, better understood using like Aristotelian hylomorphism.
I have no idea what that means. Is that like the act potency stuff?
Right, exactly. So
I don't know how when you're off the app, by the way, I can't hear you.
oh, okay. Oops. So John Bell pretty much showed in an experiment. I forgot which one.
John Bell didn't do the experiment. He came up. Yeah, you're talking about Bell's inequality. I'm familiar.
Right. Yeah, exactly. So basically he's using that to like justify the fact that oh well, we can use like Aristotle's kind of physics to to what's it called, to predict, I guess, quantum behavior. I'm not sure how like he's working with physicists, but I just wanted to know if what your thoughts are on that, if that's
I'm
something
very skeptical.
interesting.
I'm very skeptical of that.
Right.
Like I don't know.
not-
I would have to hear the the model or whatever, because that seems. I'm very skeptical of this whole business of act. Like I'm very skeptical of act potency to begin with. Like
Right.
I think that it's probably like a non-physical way of thinking about the world, and it's thousands of years out of date at this point. But yeah, I can't comment without knowing more details.
Okay, yeah, I kind of figured. That just kind of was kind of curious to see if maybe you've heard about it or whatever. I kind of had another question. It's kind
Yeah,
of
sure, fire
just
away.
general advice. Uh, so lately I've been kind of like in between math and philosophy for my undergrad.
Hmm.
I kind of had like one mid calculus test, and I'm like, oh, I'm rethinking everything about math. And I'm like, I don't know. I'm naturally good at philosophy. I think I've always, kind of just intuited decent ideas. Math, I like the proofs. Like I want to get to analysis and stuff. That's stuff that excites me. But I don't know. I'm kind of just with the whole AI solving like Erdős problems and all that. I'm
Erdos
kind of
problems are
like
combinatorics problems, which are um,
LLMs.
famously easily handleable by computers, because it typically, and not to say that something wasn't impressive, but these are typical. There's a reason why it's the Erdos problems and not like problems in analytic number theory or problems in PDEs, things like this. Like mathematicians aren't going to be out of look. Let's put it this way: if you think that you're going to have a hard time finding a job with a math degree, it will be doubly hard to find one with just a philosophy degree.
Well, so the thing is, I'm doing a double major in music education for scholarship reasons.
Sure.
I'm a violinist, so
Okay.
I mean, like even if the philosophy stuff didn't work out for whatever reason, I'm probably going to be a music teacher anyway. So I mean, yeah,
So
I
wait,
guess
I thought you said you were doing a double major between math and philosophy.
no. I was deciding between the two.
Oh,
I can't do both since the double
I would
majors.
imagine that generally speaking, you will have an easier time getting a job with a math degree than with a philosophy degree.
Right, yeah.
Like
But
just for obvious reasons, perhaps. Um,
right, yeah.
but I
Yeah,
mean,
no.
like, look. So if you wanted to do, combinatorics, then maybe don't go into it if you're afraid of AI. But like, I don't think that. I don't know. I don't think that AI would be a good reason to not get a math degree and instead get a philosophy degree.
Yeah, I think I think the reason I did bad on that calculus test was like it was at the start of the semester, and I hadn't like touched up on my algebra. In high
Sure.
school I did not care about
Yep,
math
that'll
at
do it.
all. So yeah. Anyway, I kind of had a crisis over that, and I was like, oh, rethinking everything. But yeah, appreciate the time.
Of course. Thanks for being here.
Yep.
Now, we have a few questions. I'm going to answer those, and we'll bring up another guest afterwards. So from C-Bar, how do objects work with slow rotating objects? Venus is slow. Orbits don't really care about how fast the object is rotating, right? They just don't really care, because you're not like, the rate of rotation of the object only affects how fast you're going if you're stuck on the thing. But if you're in space orbiting the thing, it doesn't matter how fast the thing is rotating beneath you, at least not until you get to relativistic stuff. Um, 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 um. Baby calc 1 is not an indicator. Yeah, that's definitely the case. If you just because you don't do well in like your first half of your first semester of calculus, it's not an indicator that you'll do poorly, right? As a math major. Have you ever seen speculative art that portrays what scientists think aliens might actually look like, in particular Wayne Barlow's work? If not, I think you'd appreciate it. I have a little bit. It's always like, and I like this. Like, this is almost certainly the case that just aliens would look nothing like anything that we've seen on Earth. Almost certainly, maybe they would have legs or arms or something like this, just because that's probably a good way to get around. But besides that, probably not much. But I haven't seen his work specifically, so if you want to post some stuff in the Discord, I'll take a look. If you like philosophy, you could follow with law school. That's true too. Philosophy degree will give your prospective employers a heads up that you'll be the most annoying person anyone has ever worked with. Go with the math degree. That's also true. There's definitely a bias there. All right, let's bring up Rin.
Hello.
Rin, how's it going?
It's going all right. How are you?
I'm doing okay. What you got for me? What questions?
Yeah. So I can never seem to hook set a bass.
Sorry to hear that. I can't help you though.
You can't help me?
No.
There's not like math in this or something?
There probably is, but I don't know anything about fishing.
Okay, man.
Sorry, bud.
I'm just gonna keep trying.
All right,
Thank
good luck.
you.
All right, let's bring up Prod.
Hey,
Prod, how's it going? You too.
I have a question about.
Did I just hear my voice in the background?
Oh, yeah, I also heard that. Sorry.
That's fine. No, you're fine. You're fine. So what you got for me?
About magnetism.
Yeah, sure. What about it?
Think about why, if there's any experiment to find out what's actually causing the force to act in a perpendicular direction to the particle's motion and the magnetic field. Because do you think the magnetic field is, I guess, in a way, not as essential as the electric and gravitational fields?
Well, I mean, they're like two sides of the same coin. So experiments generally aren't going to explain how a law of physics works. It's just going to be an experiment will show you what the law of physics is. Like you'll observe some behavior and then you will write down the law of physics that corresponds to that behavior. But experiments won't really explain how this works. If you want to look at how this works, and it seems like your question seems like it's more about why. Like it's a why question. Yeah. Like the how, I could just tell you the mathematics, right? And that would be a how. It's not physics is not really in the realm of hows versus whys. There just seems to be kind of two different kinds of forces. There's electric type forces and magnetic type forces. Electric, like gravity has this too, by the way. There is gravito-electromagnetism. So in a certain particular choice of coordinates and so on, there's a part of the gravitational force that looks like attractive or repulsive. In this case, it's always attractive, but that looks attractive like the electrostatic forces. And then if you have a mass that's spinning, that there will be a part of the force that also looks like it's sort of perpendicular to the direction of motion, or the force that, the force is kind of perpendicular to the gravitomagnetic field, and it looks like a magnetic field. So this is just a way of describing forces in a four-dimensional space-time. There's kind of, you can think of the electric part as kind of the time part, and the magnetic part as kind of the space part.
Okay.
And by the way, all forces have this. Yeah. It's gravity, electromagnetism, the strong force, the weak force. They're all going to have electric pieces and magnetic pieces, even though it's not the same as electricity and magnetism. It's just kind of an analogy.
Right. I think there must be some kind of reason. I know that's kind of
what kind of reason do you think is like, what kind of thing would be a reason that explains? Like, give me a prospective reason, I guess.
When people were first looking at it, they were thinking about the ether. They were thinking there were small particles, or I guess not physical particles, but some kind of ether with units that spin. And I forget exactly how you'd explain it in words.
So let me ask you a better question. Why is it that, so why do you have this question about magnetism, but you don't have a similar question about the electrostatic force?
I know quantum mechanics would explain electrons and where the charge comes from.
Quantum mechanics also explains the magnetic field, right? And the electric, it explains both. It explains them both equally, like in a similar way.
Okay. Is there a reason why it points in a different direction though? Because it's related to the
different direction relative to what? Is there a reason why the electric field points in a different direction?
I say always points directly between the charges instead of perpendicular.
Yeah, so why that direction instead of perpendicular to them? Perpendicular to the line connecting them. Like, no, I mean, the point is that like, magnetism shouldn't be thought of as somehow less fundamental than electricity. They're just different. Now, maybe because we're so used to things like grabbing onto each other that we're used to like things pulling towards each other or repelling away from each other, and magnetism seems spooky. But that's just like a problem with our intuition. It's not really like a problem with the way the world is.
Okay, yeah.
Does that help? Well, let me clarify. It doesn't help, but at least it hopefully assuages you that this is not the kind of thing that, like, you're right to think that it's weird. You're wrong to think that it has an answer.
Yeah. That's something that's a little frustrating about theoretical physics. But yeah.
One potential explanation that I could give you is, if you look at the math, if you look at the math between electricity of electromagnetism, like the deep math, not the stuff that you learn as like a freshman in university or something. If you look at the deep math, they basically look the same. Like the formulas are identical, or nearly identical. They're not exactly identical, but they're nearly identical between electricity and magnetism. It's just because magnetism is in some sense spatial, whereas electricity is in some sense temporal, that you get like this apparent big difference out like when you kind of zoom out. But that's a distinction between space and time, and then you could ask, well, why is time different from space? And well, now we're back to the same question.
Yeah. Okay. Thanks for your time, and good luck
Of course.
with the treatment.
Appreciate that. All right, let's answer some questions. We have a super chat from Big Fat Tank with the 7 Canuck bucks. Very much appreciated. If a photon has h-bar angular momentum from spin, how can one photon impart 2 h-bar angular momentum in a quadrupole SD transition, not spin vortex beam? I would need to know the specifics, but like, look, so if your angular momentum is h-bar, and then like, I'd have to know the specifics here, but like if you have a reflection, for example, what I'm thinking of is, imagine a reflection of a photon for its linear momentum. The reflection will impart twice the linear momentum of the photon, right? I imagine that a similar thing could happen for a photon transferring its angular momentum to an object, and then it would come away with the opposite angular momentum. So that would be 2 h-bar. But otherwise, I've like this seems sufficiently specific that I would actually have to go look into what you're referring to. Okay, so you're talking about a quadrupole SD transition. So you're talking about a transition between the S and D orbitals, I imagine. I don't know what you mean by the spin vortex beam. I'd have to look into it more. But if you want to DM me on Discord, we can talk if you have a question. Let me make sure I didn't miss any questions. Have we ever found out Dr. Blitz's favorite shark? I'm quite fond of, what is that one shark? I'm quite fond of white-tipped reef sharks and black-tipped reef sharks. They're quite good boys. So here now I can actually get through all the questions. So I'm going to as a crazy cringe question with all the potential in the universe. How likely do you think there is out there? How likely do you think there's life out there and bonus sentient life? I think that both are quite likely, just not close to us at all. As we could be surrounded by unlocal quantum mechanics, maybe we're submerged in it as an emergence into the depth. Gravity naturally is some consequence, though hard to find the coupling. I don't know what that question means. I don't know what it means to be submerged in quantum mechanics. Like, what we are quantum things, right? From Matthew Williams with the 5 Canuck bucks, what is the universe expanding into? I've had it explained as it's expanding into itself, but my mind can't comprehend that. It's not expanding into anything. In standard cosmology, there is nothing there. It's not like that there's emptiness outside the universe. There just is no such thing as outside the universe. So the expansion is not happening at edges, right? There's no edges to the universe. There's no reason to think that there's edges anyway. Rather, the universe, the distance between all non-gravitationally bound objects is growing. The distance between them is growing. That's what we mean by the universe is expanding. If the universe has finite volume, that finite volume is growing with time. Reality is indeed confusing. The Greenland shark is also pretty great. I like the Greenland shark a lot. Whale sharks are good too. Electrons up and down quarks makes a soup that matters. True. Submerged like the spaces stretched between quantum mechanics. Quantum mechanisms. Quantum mechanisms are not like a physical thing. All right, let's bring up another guest. Let's talk to Kubanito. Kubanito, how's it going?
Hello, Dr. Blitz. Nice to meet you, man. You can call me Dante.
Dante. Okay, Dante, what you got for me? What questions?
My brother, I have at least 2 questions. I'll make them quick. I know a lot about black holes, but not so much dark matter. My question to you is there any correlation that can be made between the two or no?
Yes, there is. It's speculative. We don't know that this is true, but it is speculated that what we think of as dark matter is just a whole bunch of tiny black holes. This would be called, This is the Macho hypothesis. Massive astrophysical compact halo objects. Basically, it's plausible, we haven't proven this, but it's plausible that in the very, very early universe, a bunch of tiny black holes were made, and they would have been big enough that they would have survived till today. And that stuff would have been what we think of as dark matter. It hasn't been ruled
Wow,
out entirely,
okay.
but it's not proven.
Okay, gotcha. And my other question is, I'm gonna try and phrase this the best that I can. I'm not too well versed on the formation of stars, but obviously stars have a center of mass, and they have immense gravity. Let me see how I can phrase the question. When does the gravity, I guess, start, or let me see how I can phrase. When stars are forming, which I don't know I think it's nuclear fusion. I think it's how they're formed. And its center of mass, when a star implodes, and becomes a black, if it's massive enough, right, it becomes a black hole, and the point of it is a singularity. When does that occur during the star's lifespan? Like, when does that point of immense gravity start? If you
mean
get my
like
question.
the singularity, or when does the star's gravity start?
There you go. Yeah, when does the star's gravity start exactly?
So it doesn't. Stars form in gas. Stars form from glass. Stars form in gas clouds. And so that gas cloud has mass. It's going to have gravity. So if you were outside that gas cloud and just hanging out outside of it, you would feel the same gravity whether the star forms or whether it doesn't form. Now, what often happens is star formation needs to be triggered by something. And there are a few different ways that you could trigger star formation in a gas cloud, because often they'll just be kind of like stable, because if the gas cloud is too hot, then it won't want to collapse, because the pressure will increase and that'll make things want to push out. So sometimes you'll have like a supernova go off somewhere else, and that'll push a shock wave through it, which will trigger gravitational collapse. And so because the gas cloud itself has gravity, you can trigger a collapse of that gas cloud into a star, and that'll create a runaway process, and you'll end up with nuclear fusion at the center because it gets hot enough and high enough pressure. One sec, sorry.
Interesting. Okay.
And so the point is if you're outside the gas cloud, even after the gas cloud collapses into a star, the gravity will be the same. All you've done is just rearrange what the matter's doing inside the gas cloud, but it's still the same amount of matter. And the same is true for the black hole, right? It's still the same gravity. It's just now it's still the same gravity because it's still the same amount of stuff. It's just a lot more compact.
Right. Okay. Okay. I never had it explained to me that way. I've been scouring, the internet and trying to trying to get an answer for it, but it's a lot of tough words and vocabulary that's used, so it's a little tough for me to read. I'm not an academic anymore.
That's normal.
So, but okay, great. I know those are simple answers. I'm sure they're much more complicated. It's a lot more explaining to do, but I appreciate it. At least that's something.
I appreciate you being here. Have a good one, man.
All right, thanks, sir. You too, man. Bye.
Bye-bye. From Cloud of Time with the $10, I like your demeanor and content. Just sending this to support, no question. Well, I appreciate that. Oh, my uncle called me again. Wait. Oh, no, that was yesterday. Oh, I got a phone call from... Who called me? What is that number? Okay, I'll look at it later. Sorry, I want to make sure that I don't miss any of the text questions, because you guys are super fans or members on YouTube. If you want to send questions, it's like $5 a month or something. So, it's a good option. So I guess you reject any possibility of more axes than 3D XYZ. No, I don't reject that. But that's not what quantum mechanisms are. Quantum mechanisms aren't more axes than 3D XYZ. I just don't understand the relation between the two. It's not an unfortunate acronym. It was done on purpose. There's machos and there's WIMPs. Machos are massive astrophysical compact halo objects, and WIMPs are weakly interacting massive particles. These are the two different kind of standard stories for what dark matter is. I want to make sure I don't miss any questions. The gravity is the same for the cloud or the star. Is the inertia the same if it's activated, or does that jump up? So the point is that if you're outside where the cloud is, whether or not the cloud collapses into a star, or whether it stays just a cloud, or whether it collapses into a black hole, the gravity that you'll experience from far away will be the same, because it's the same amount of mass, unless it gives off some mass and shoves it out beyond you. But the point is if there's the same amount of mass there, it doesn't matter. All right, let's bring up our next guest, Mr. White 369. Mr. White, how's it going?
It's going all right. How are you?
I'm doing okay. Mr. White, what questions you got for me?
Sure. Just a brief. So would you subscribe to the idea that the moon has a relationship with the tides, going, high tide or low tide every day, all day? You do?
Yeah, the moon is involved in the tides. Yeah.
Okay. Oh, all right. So what type of relationship to the water do you think it's having?
It's a gravitational relationship. It pulls on the water.
Okay, so it should then affect our bodies the same way, right?
No. So
Well, no, you can't pick and choose.
this isn't a
Water's
debate.
water,
I'm telling you
right?
how. Look, Mr. White, this isn't a debate. I'm telling you how this works. You ask a question, I'm going to answer it. So the reason why the tides are so significant on the Earth is because it's not just because the gravitational strength of the moon. It's because of how the gravitational strength of the moon differs from place to place on the Earth. So gravity gets weaker the further away you are. So the far side of the Earth, from the moon's perspective, is going to have less gravitational pull from the moon than the near side will. And so because the Earth is so big, that difference in gravitational pull between the two sides of the Earth, that's what causes the tides. You have the far side, which has you have the far side, which is going to have less gravity, the near side, which will have more gravity, and so the water will flow to the places where the tides end up being. Us as humans are very small,
I understand
so the
that.
amount
That's a pretty big. That's a pretty tall order. You're
us
saying
as
there.
humans, we're small. So the difference in gravity from the moon between our heads and our toes is negligible. Has basically no effect.
That I'm not buying that, because water
Okay,
is
you don't have
the
to buy it. That is the
mechanism
answer.
right there. So it doesn't come down to how big they are or how
It
small
does.
they are.
It comes
as
down
far
to
as its
how far.
influence.
It comes down to how widely spread out that water is, because then you can get tidal effects. The tidal gravitational effects is what they're called.
Well, I mean, that's a pretty tall order. You got this
Okay.
every day.
I'm sorry you feel that way. That is the answer.
I mean, you guys just dodge this so much, and I don't understand.
Mr. White, this isn't a debate live. If you don't like the answer, you can go complain to your fellow flat earthers or something.
It's not even about that. It's not even about.
But if you have, do you have another question, Mr. White?
It's just getting a viable answer. That's all.
The answer is viable. It works out mathematically. If you don't like that, I'm sorry to tell you. I don't know what to tell you besides that.
You're gonna have to show me that mathematical question there.
Okay, you can go. I mean, Google is free. He definitely came up because he wanted to debate. I'm pretty sure he was a flat earther too, right? But yeah, so to be a little bit more specific, you have the weakest pull from the moon on the far side, the strongest pull from the moon on the near side, and then sort of a balance on the, on the places between that. And so the parts of the Earth that have the weakest pull, the Earth is going to be pulled more strongly than the water. So you'll have a clump on the backside. Water will flow towards the backside and towards the front side. So you'll have low tide in the middle, because that will have a pull actually inwards towards the moon. I can actually, let me just show you a diagram. It's a really neat way to, I just have to find one with the forces on it. Yeah, here we go. So here's the relevant picture, right? Oops. Whoop. What just happened to that text? What just happened to that text? Something horrible has happened. Oh boy. Transform, is it backwards? Flip? And then rotate? Okay, I think that we're good, sorry. So the relevant thing here, the relevant part of the diagram, is this thing that's happening on the left. So see those arrows? Those represent the forces. Those arrows represent the forces on the Earth from the moon. So you see that the part of the Earth that is closest, the part of the Earth that's closest to the moon has the strongest force, the part of the Earth that's furthest from the moon has the weakest force. And notice that the parts of the Earth that are in the north and the south, they have forces that are somewhat inward, right? they're horizontal, but also a little bit inward. And so what you're going to see is that you will have basically essentially a downward force in the on the this part, kind of in the middle part, and then you have an upward force on the edges. And the reason why you have an upward force here is pretty obvious. It's pulling it closer to the moon more than the Earth is. But the reason why you have an upward force over here on the water, which is why you get high tide on the other side, like over on this side, is because this side of the Earth is being pulled on less than the middle of the Earth. So the Earth is actually dragged closer to the moon less than the water is. So the water ends up being effectively higher. So you end up with high tides on either end of the, if there were no continents. The continents make it a little bit more complicated, but if it was just water, you would have high tides on the near end and the far end, and you would have low tide on the ring the ring separating the close end and the far end. That's how tides work. It's quite neat. And EB, welcome to level 1 subscriber or member mode. Thank you for becoming a member. I appreciate you. Sorry, I just got to make sure I don't miss any questions. Okay. I have a question. Do I just post it? Yep. He didn't pay for an L. He just joined. But well, it's pretty simple. I think we have theories of potentially flat universe topologically and such, and time can potentially be infinite too. Wouldn't the fact that we can create partitions in time or space mean that theories of infinite anything be undone, since you can't partition anything infinite? You can partition infinite things. We do it all the time. You can divide up the real number line, which is infinite, into integer chunks. There's no issue there. Tides are just water masses pulled. The difference of the forces are secondary. Earth has 12,000 kilometers. Moon is 380,000 kilometers. So the pull difference is under 2% or so. No, but that pull difference is the relevant thing. It's the difference in force that is relevant. I always assume that if you squeeze anything in any direction, unless it compacts the perpendicular sides, we'll have to bow outwards. Yeah, that's roughly it. That's similar. It's essentially that tidal forces squeeze you in the perpendicular direction, stretch you in the longitudinal direction. Yeah, so the explanation that I gave for the tides, that is like the simplified model of the explanation, which works perfectly well if the Earth didn't have continents. The thing is the water has to flow from that ring. So imagine that you have your Earth here. You have the moon over here, right? So this side of the moon has a high tide. This side of the Earth has a high tide. This side of the Earth has a high tide, and then low tide is all the way around here. And if there were no continents, the water could just flow from that ring to the high tide and the low tide, and it would be fine. But we have continents, so that water is going to flow in a more complicated way because it has to move around the land. And so what that means is that you end up with harmonics, and so it's not as simple. There are actually some places with only one high tide a day rather than two. There are some places where the high tide is huge, where the high tide is where there's basically no high tide, and that's because of the dynamics of the water flowing around the continents, along with the rotation of the Earth. The sun also does contribute to the tides. Yes, that's true too. All right, let's bring up our next guest. This person doesn't, I want to make sure I didn't miss any super chats. This person doesn't have a name, but that's fine. Hello, how's it going? Can you hear me? Yeah, I can hear you just fine. How are you doing? I'm doing okay. What question you got for me?
I had a question on the physics of consciousness and whatnot, and just to see what your opinion is, because I'm doing research in neuroscience.
Mm-hmm.
And it's just like theories like Roger Penrose's, it's just like, doesn't really make sense, or like, I can't like it's not like, I don't know how to explain what I'm trying to ask.
That's gonna make it hard for me to try to answer what you're trying to ask.
Well, yeah, it's more, do you understand how these theories are? And because they're quantum mechanics theories.
Yeah, I don't think nobody in the physics community really takes it seriously. And so as far as I know, nobody in like the neuroscience community is really taking it serious. Like there's a small amount of people who are, but it's like a very, very fringe.
Well, I know you want to focus on materialism specifically and whatnot.
I mean, this is a material theory, right? This is not. So even if like this isn't like an ideological thing. It's just like the evidence for this idea, this OR idea, which by the way is mostly coming from an anesthesiologist, not coming from Roger Penrose. Roger Penrose is just talking about gravitational collapse causing, or gravitational effects causing quantum collapse. This is a material idea, and there's just not really good evidence for it.
Okay, I guess, yeah, never mind. I guess my question really wasn't.
Sorry, I can hear you. I just gotta open my door really quick.
I guess my answer wasn't something that is with a definite answer or whatnot. It's more of like, I guess, a philosophical type thing.
Well, I'm not a philosopher, so I can't help you there.
Yeah. Well, I figured that you might have some like opinion on at least like OR, obviously.
My opinion is that it's fringe, and the only reason why anybody's even talking about it is because Roger Penrose is brilliant. But brilliant people can have bad ideas too.
Yeah. All right. Thank you.
You're welcome. Sorry to deflate your balloon. For 21st century consciousness stays non-physical. Penrose looks at microtubules and neurons. Penrose tells classical physics doesn't make the calculation capacity. What are we going to do when antibiotics stop working? I don't know. Ask a epidemiologist. All right, let's bring up Matthew Fulmer. Man, I got that grumbly tummy. Matthew Fulmer, how's it going? Matthew, how's it going?
Good.
Glad to hear it.
Is the audio quality good?
Yeah, it's fine. Matthew, what question you got for me?
So this is the first physics question I can't figure out, and I've asked friends. It's very simple for someone at your level, I'm sure. But let's say you have two objects traveling away from you at 51% of c.
Mm-hmm.
Everything seems to line up right there, unless you assume that there's somebody on one of those objects looking at you. You're traveling away from them at 51% c, and the other object is at 102% c, and that doesn't make sense.
It's because velocities don't add the way you think that they do. So at low speeds, velocities add no problem. At relativistic speeds, they don't add that way. And there's a nice formula for it. 51% is a hard number to work out explicitly for me. To like, I could go punch it into a calculator if I wanted to. But there are handy calculators there are calculators that you can punch in online. I just Googled one, found a calculator. So from the perspective of one of the people that's traveling at 51% C, the other one will be traveling at just under 81% C.
Okay, and that's due to like
time dilation, length contraction.
Traveling really, really fast.
Yep.
Okay. Yeah, I've got a friend who's majoring in physics. I posed this to him, and he said,
"What year is he?
The books for that."
What year is he?
I think he's in his sophomore year.
Okay, he may not have done special relativity yet.
I think that it's right at the level that he's going to be doing this year. So he was excited for the question, but also he couldn't answer it. And I'd like to be able to come back to him with the answer and maybe help him out with his progress on his degree.
Tell him to look up relativistic velocity addition. That should help.
Okay, thank you very much.
Of course.
One last thing.
Sure.
It's my birthday, and I'd appreciate a happy birthday from you.
I'm not going to sing for you, but happy birthday, Matthew.
That's all I wanted.
I hope it's a good
one.
one.
Have a great rest of your day.
You too. Take care. And let's get a big old happy birthday from the chat, if you're here. I hear food is a good cure for the tummy rumbles. Yes, indeed it is. But I have this live stream, and then in about 15 minutes I have a meeting. So, well, I mean, I can have snacks, of course. All right, let us bring up, we have a guest who's in the Discord waiting room. Let's bring up It's Dundee. It's Dundee, how's it going?
Hey, how's it going? Can you hear me?
Oh, why can't I hear you? Oh, I can't hear you, but everybody else can. One sec. Go ahead.
Okay. Oh, thank you. I've got a question. I got a new information, or at least it was, for me it was quite a new information yesterday, or a couple of days ago, and I hope that maybe you could explain it to me in a way that I can actually understand it. So the information is that I heard that the universe is actually flat, and how should I imagine that?
Yeah. So I know what you mean. I understand the confusion. It does not mean that it's two-dimensional. What it means is that the intrinsic curvature, so space-time is curved, and what you can imagine is at a given moment of space, at a given moment in space-time, you can imagine that you have space, which is three-dimensional. It means that the three-dimensional space is not curved. And when I say curved, that means a very specific thing mathematically. It means that, in particular, there are no tidal gravitational effects absent matter. It means that there are no, scalar gravitational effects, again, absent matter. So that's what it means. It doesn't mean that it's two-dimensional.
Yeah. No. I basically I just can't imagine in my head how could a three-dimensional space be flat.
Just think of it like. You know how, like, have you ever been in like a, I don't know, like a video game where you can move in 3 dimensions? It's just that. Assuming there's no gravity, it's just that.
Okay. Okay. I see. Okay, that makes it closer to understanding. Okay, no,
good.
Thank you very much.
Well, thanks for being here. We have a question from Big Fat Tank. Would modified Newtonian dynamics require graviton to have imaginary mass for there to be increasing in strength with distance? Modified Newtonian dynamics, as far as I can tell, is not compatible, at least not yet compatible with quantum field theory. It's just not. So they can't even talk about gravitons. The people who do MOND, they're not at that level at that point. All right, let's bring up Ethan the Aussie.
G'day,
Ethan.
Dr. Blitz, how you doing?
I'm doing all right. What question you got for me?
So when it comes to the Young's double slit experiment, I was just wondering, like, what is your... I can't wrap my head around the idea of particles acting differently if they know they're being observed or not.
Fortunately, that's not what's happening. At least that's the mainstream view is that that's not what's happening. What's happening is that everything is always a wave. Those waves can interfere with those waves can interfere with themselves so long as the waves that are doing the interfering are the same kind of thing, and they're in some sense in the same state. However, when you interact with something, you become entangled with that thing that you're interacting with. That's what an interaction is. So if you look at something or if you measure something, you are becoming entangled with it. And so now, if the way that you become entangled with, that wave that wants to pass through the two slits depends on which slit the wave is passing through, then now the pieces of the wave that are coming through the two slits are no longer the same thing because they're entangled in different ways. And so they can't interact with each other. They can't interfere. So they can't cancel out. They can't add up. So you just end up with two blobs. It doesn't have anything to do with knowing they're being watched. It's just a feature of the way that waves can self-interact. They can only self-interact if they're the same kind of wave, if it's a wave in the same thing in some sense. And interaction prevents that from happening.
Wow. Okay. Thank you.
Of course. Anything else?
No, that's all. Thanks. Keep it up. I enjoy watching the lives, and have a good one, man.
All right. Take care. I feel like I got a notification somewhere, and oh, never mind. I know what that is. All right, let's bring up Midnight Alchemist. Midnight Alchemist. Midnight, how's it going?
Good. How are you?
Doing all right. Midnight, what question you got for me?
I don't have a lot of knowledge in physics, but I'm just curious, at what point does physics, like, there's relativistic physics, so at what points in our universe do those laws, our known laws, break down? Like, at what scale? Is there scale ones? Is there, like, time ones? You know what I mean? Like, what points are we, like, everything breaks down at certain areas?
So... do you mean like the kind of physics where the kind of breaks down where we say that, like, physics breaks down at the center of black hole kind of thing? Or do you mean like how classical Newtonian mechanics stops being Newtonian and starts being relativistic?
Yeah, like I guess how many different points are there in which different rules start taking place that supersede? Yeah, are there a lot? Like,
it's probably not a number that you could enumerate. So there's kind of two two things that are separate here. The places where physics actually breaks, like at the center of a black hole or at the Big Bang or whatever, those probably aren't like real things at all. Those are probably just like we need better physics in order to understand what's going on. But there are always different regimes where we have better ways to describe what's going on. So for example, imagine that you had like, I don't know, water coming out of a faucet, right? So in principle, that water coming out of a faucet is just like a whole bunch of water molecules, and they're like bumping up against each other, and then there's gravity, which is described by the curvature of space-time. So
And
if you
flow
wanted
rates. Yeah.
you could describe that whole system using the curvature of space-time and individual quantum particles moving in the curvature of space-time. And it would be horribly complicated. It would be correct, but it would be horribly complicated, and we don't have a supercomputer big enough to do that. Alternatively,
So we chunk it. We chunk it.
We chunk
simplify
it. That's exactly what we do.
Okay.
We say, well, we don't need to worry about this curvature of space-time because Earth's gravity is not very big. We can just use Newtonian physics. And we don't have to worry about the individual quantum interactions of these hydrogen molecules or these water molecules, because the average effect is well described by fluid mechanics. So instead what we do is we write down a new law, which is sort of a zoomed out version of that, the more complicated thing that is now easier to solve. The thing is there's not a hard barrier that divides where, quantum mechanics becomes more accurate and classical physics becomes less accurate. It's not like a hard cutoff. It's just a gradual approximation, and the approximations get better as you get further away from, whatever the relevant regime is. So, for example, if we're doing calculations for gravity on the surface of the Earth with like a cannonball, you don't need to account for the curvature of space-time, right?
If you're
It's not
trying to land on
relevant.
the moon, the scale is large enough where you get errors.
No, actually, you can land on the moon with just Newtonian physics. If you want to describe, I don't know, landing on a planet orbiting a black hole, now you might have to take that into account, because now the dynamics are sufficiently complex, or the effects are sufficiently big that you have to worry about that. But there's not like a hard cutoff.
Right. So as human,
You're fine. Go ahead.
I'm fascinated with complexity.
Mhm.
And how we as humans value like increases in complexity. I've noticed that in like many facets. Is there like within physics, is there like we'll never understand the complexity due to the limits of our own comprehension? Like as a human being, you are in theory limited to only a certain limit, as like a cat is limited to its understanding of the universe. Like
maybe, we don't know.
That's
I mean,
wild.
I don't even know if that's in principle possible to know. Like, is it possible for a fish to ever know that it couldn't understand calculus? It probably isn't.
It's not even aware
Right.
of its existence. And so like there are things then you can then draw that out and say, as human beings, we are limited by being a human being.
Well, sure, but it doesn't therefore follow that there are things we will never understand. Like, it's possible that we happen to be smart enough that we will eventually understand everything. It's also possible that there are things that we will never understand. I don't think that we can predict that. I mean, okay, let me rephrase. If it's the case that we can understand everything, I think that we could know that. But if it's the case that we can't understand everything, then we will never know that.
Yeah, because it's one of those fallacies or one of those. Okay.
It's like a trap. Any other questions you got for me, Midnight?
Nope, that's everything. Thank you very much.
Of course. All right, we have enough time for one more guest, and then I got to run because I have a meeting. Let's see if Green joins. Didn't they recently find a sentient fish? I don't know. Gruck Green, how's it going?
Hi. I was wondering why the Big Bang didn't become a black hole instead of exploding. Yeah,
so the black holes only form when there's when there's a lot of mass here, and then there's not a lot of mass outside of there, right? You have to have, it's not just enough to have a lot of mass. It's not just enough to have a lot of density. You need a non-uniformity of that density. You need to have a lot of density here and not a lot of density outside. But the Big Bang, as far as we can tell, was extraordinarily uniform. There were hardly any overdensities anywhere. So there's just like a question that you can ask yourself is, if it was going to collapse into a black hole, where would it collapse? If it was uniform, where would it end up? And because there's no answer to that question, the only conclusion is that indeed it won't collapse.
Okay. Because I've always had the thought that it would just collapse into itself.
Nope,
since
doesn't
there
have
is
to.
nothing around it.
Well, no, the point is not that there's nothing. It's not like there is space, but there's nothing in that space. There is no space around it. It is everything.
Kind of breaking my mind, to be honest.
So don't think of the Big Bang as being there is like a really dense place, and then there is nothing, but there's and then away from that there's empty space. It was all of space was in that tiny dense place. There was no, not even any space outside of it. That was all of the space that existed.
Oh, okay. Oh, I think I understand.
Well, I hope so. Green, I'm gonna let you go, but thanks for being here, because I have to answer a few more questions and I gotta call it a day. We have a super chat from Garain with the $5. Will all orbits eventually collapse due to gravitational waves bleeding off energy, or just apolitical to massive objects, or just applicable to massive objects like black holes? Yes, eventually they will. That is absolutely true. They do bleed off gravitational waves. They do bleed off energy by gravitational waves bleeding off energy. It's just very, very slow, like trillions of years for like the Earth going around the sun. As far as the experiment went, I'm pretty sure yes. As far as I remember, the fish could recognize that it was looking at itself in the mirror and not another fish. Right, but that's not enough to know that it doesn't know calculus. All right, y'all, I'm going to end the live stream here. I'm sorry if I didn't get to all of the guests who are waiting to ask questions. I do these once a week. I'll bring up guests once a week, but I have a meeting this week, so I have to cut it short. Thank you guys so much for being here. Remember to join the Discord server if you want to, get announcements for when I'm live next, for when I post videos, etc. It's discord.gg/drblitz, Dr. Blitz. Or you can go to my website, which has a link to all of my socials. It's just blitz.phd. You can check out all my socials there. And if you want to ask text questions because you're too nervous to join the box, next time we have one of these, become a member on YouTube. It's like $4 or $5 a month. It's a great way to support me, and it really encourages